Next, we turn our attention to testing hypotheses about population means. Just as the secret to testing hypotheses about population proportions was the sampling distribution for a proportion, the secret to significance testing for population means is also the sampling distribution of a sample mean. You may recall from Chapter 7 how Gossett described this distribution using his now famous t-distribution. The shape of this sampling distribution varies as the sample size varies and becomes increasingly like the standard normal distribution as n approaches 30. The big idea behind significance testing for population means is exactly as it was for proportions. The only difference is how we calculate the test statistic. This time it's the familiar t-statistic, whose formula is shown on the screen. So let's be brave and jump right into an example. One of the major reasons for concern about how much TV children watch has to do with potential links to obesity. This study was designed to test the hypothesis that the average time that a third and fourth grader watches TV exceeds 2 hours a day. So data was collected on 198 such children, and the mean number of hours a week these children watch TV was found to be 15.4 hours with a standard deviation of 14.16 hours. The question is, does this data give evidence that third and fourth graders on average watch more than 2 hours a day of TV? Now, since the data was summarized as hours per week, we will rephrase the claim to ask if these children watch on average more than 14 hours a week. So the four-step process we use to test proportions is still valid. This time the parameter in the null and alternative hypothesis is not p, but rather mu. And we will be testing the null hypothesis that third and fourth graders watch on average 14 hours of TV per week against the alternative that they watch more. The test statistic is now a t-value, and we calculate it by replacing x bar by the sample mean of 15.4. We replace mu by the value in the null hypothesis, namely 14, and in the denominator we use the sample values of s and n. When all is said and done, the value of t is 1.4. When conducting tests of significance involving population means, we do not use the standard normal calculator to determine p-values. This is because the sample mean follows the student t-distribution. When we use the online t-calculator, we find that the area above t equals 1.4 is 0.81. Since 0.81 is not less than 0.05, we decide to fail to reject the null hypothesis. And we don't have any evidence from this study that third and fourth graders watch more than 2 hours of TV per day. If we were to follow this up by establishing a 95% confidence interval for the average hours of TV that third and fourth graders watch per week, we would find that that average with 95% confidence is somewhere between 13.4 hours and 17.4 hours. Since 14, the number in the null hypothesis, falls within this confidence interval, it is reasonable that we decided not to reject the null hypothesis. It is possible that children in third and fourth grade watch, on average, 14 hours of TV per week. In this next study, we are interested in the mean number of hours of sleep that students at a particular school get each night. A school psychologist has claimed that it is 8 hours a night. Data is collected from a random sample of 15 students, and we are about to test the psychologist's claim. The first step is to use StatCrunch to calculate the sample mean and sample standard deviation. Next, we set up the null and alternative hypotheses. The null hypothesis agrees with the psychologist's claim, and the alternative says it is incorrect. A two-sided alternative seems appropriate here, since there is nothing in the statement of the problem that would lead us to believe that her claim was either too high or too low. Next, we substitute into the now familiar formula for t and find the test statistic is a negative 2.85. Using the online t calculator, we find the area beyond plus and minus 2.85 is 0.013. This is the p-value. Since p is less than 0.05, we decide to reject the null hypothesis. And since the test statistic is negative, we also decide that the population mean is less than 8. Putting it all together, we conclude that the mean number of hours of sleep that children in this school get each night is less than 8 hours, and we are careful to include the p-value of 0.013. Following this up with a 95% confidence interval, we can further state that the mean number of hours that children in this school get for sleep each night is somewhere between 5.6 hours and 7.7 hours. Notice this interval contains values that are lower than the hypothesized 8 hours, so it is reasonable that we rejected the null hypothesis.
So I wanted to say a little bit about the calculator we're using this semester to get critical t-values. The calculator actually exists within StatCrunch. You would look at the Stat menu, and then pick Calculators, and then pick the t-calculator. You're going to be asked for a number of degrees of freedom. Well, in this particular study, there were 198 children, so that was 197 degrees of freedom. We calculated a t-value of 1.4. Our alternative was that they watched more than 14 hours of TV per week. So the reported area above our calculated t of 1.4 is 0.0815. That number is greater than 0.05, so we are going to fail to reject the null hypothesis and claim that there's no evidence in this data that the children watch more than 14 hours of TV per week. Another quick follow-up on the study of sleep time of school-age children. We're going to find the critical t-value using the t-calculator on StatCrunch. We have a two-tailed test. They either sleep 8 hours a night or that they sleep something other than 8 hours a night. So we clicked on between. We entered the critical value that was calculated, plus and minus 2.85. 15 children, 14 degrees of freedom. So the area between those two critical values is 0.9871. But of course, we want the area in the tail, so we're going to subtract that 0.9872 from 1 to get the area in the two tails, which is the critical area, and that p-value is equal to 0.0128, which is why we rejected the null hypothesis, because it was less than 0.05.